Hello, welcome to another problem session. Today we have a really important problem, and conceptually, this is probably one of the more important problems that we'll do in rotation. So let's just look at a background you will need to solve this problem. Okay, so the background you need is, so if something is just purely rotating, if the axis is it's a fixed axis and it's purely rotating, then you have very simple the angular momentum is about this axis, so axis A. So this, suppose this is z axis, so LZ is just I ZZ times omega z. So this is one of the principal axes. It's rotating about that, and so sometimes it's just simply just I 0 omega. You just write like that, and you just write just L instead of doing all of this extra stuff. So this is the pure rotation about principal axis. Well, if you have a rotation and translation, by translation I mean translation of the CM. So you have a rotation and translation in the same. So as is the case here, if you look, this is the CM. CM is translating, and this thing is also going around. It's rotating and translating. So this is, we'll call it rotation, and we'll call this translation motion. When you have something like this, then you can prove that L of Z separates into two parts. Okay, so what does it mean? So LZ is as if it's just rotating through a center of mass. So it will have a term that's a, let's call it I0, and let's call it omega, and axis through center of mass. So there's the z-axis is going through the center of mass. So plus what you have is as if the entire mass was a point particle placed over there, so with a velocity v. So you will have this vector will be RCM, center of mass, cross this velocity vector. So you'll have a total mass placed, this is the CM, cross R cross P. So RCM cross this, not this. And because we're looking at the Z component, we just take the Z component, this cross product. So this is the separation. Actually, this separation happens also for kinetic energy. So if you look at the kinetic energy here, this is kinetic energy, will be simply kinetic energy of rotation. This will be half I0 omega squared. So I0 is this, the same thing. Over here, kinetic energy will separate kinetic energy of axis through this rotation, axis through CM plus off CM motion. it's going to look at half I0 omega square, this guy over there, plus half m VCM square. So this separation is very important in many problems. And if you just have pure rotation, you just have pure problems. So you need to have this background to answer this problems like that. So with that background, now I'm going to solve this problem. You may try to do it yourself first. Now, if you have now that you have the background, okay. Okay, so if you are going to study more theory, how the separation takes place, the calculations and things like that, you can go visit this free website. To this problem, let's look at the rolling motion. So it's at some time it's over here. Let's call it is over here, and just follow one point at the edge. You will let's look at another ink. I'm going to follow it here, and as this moves, as this guy moves over, as this distance moves over here, now so you can see it used to be in that direction. Now that green point, this point is moved over there. So this is the amount of angle it would have gone, and the distance, this distance will be equal to the arc distance it covered. So along the x, this delta x and this delta theta will be related. So delta x, delta t will be related to r times delta t. So this v will be equal to this. So omega r will be, in terms of magnitude, equals to big V. This is of the CM. This is of the CM. So that's the relationship here, right? And you can see this is rotating in a clockwise fashion. And if the z-axis is coming out, then if I look at the axis, z-axis this way, then the rotation sense is clockwise, which means I'll get a negative value for just the pure rotation. So L of z will be equal to, you'll have a L z of rotation about axis, say call it A, about A through CM, plus this RCM cross mass times V along the z-axis. So RCM, it has a, over here RCM, it has some XCM I hat plus some YCM J hat, I hat, and J hat as unit vectors along this axis. So the whole thing is going in the XY plane. Then, and the V is simply V I hat. So when you take a cross product, this doesn't work out, and YCM is simply the distance R. So this is equal to just R. So RCM cross V is YCM times R, which R times V, R times V. So we can take a right hand, and it's actually towards the negative z-axis. So, and direction is negative z-axis. So this is j hat cross k hat is minus j hat cross I hat is minus k hat. So that's the negative z-axis. So we this one, on the other hand, is half mr square for moment of inertia. This is I0, and we have omega. So this and this is going to be, we need to decide plus or minus what is the sign. Is rotating about counterclockwise, which clockwise, so this is negative. So I got a negative for this, and using this I got a negative for that, negative mRV, and the V, we just leave everything, but V is given as a V. We can convert this R times omega into one of the R's as a V. Omega R is equal to V, and so we get minus half mRV minus mRV. So the answer is minus 3/2 mRV. That's the answer. Okay, I hope this is clear to you. What helped us is in this problem is the separation that we expect when there is a rolling motion. So that's point number one. And point number two was how we're able to relate the angle it rotates and the distance it travels. So this was another, so this is point number two. So using these 2 points, you can solve a lot of rolling motion problems.